Moving on to proposition 16. In any triangle, if one of the sides be produced, the exterior angle is greater than either of the interior and opposite angles. So what's the claim here? That if we have some triangle, let's take this lower side and just extend it. And let's think about this exterior angle right here. The claim is that this angle is greater than both this angle and this angle. Notice he says interior and opposite. Certainly not greater than this one of necessity, because you can just as well draw this angle to be an obtuse angle, and it's going to be false. And let's draw this out. Let ABC be a triangle, and let one side of it, BC, be produced to D. Okay, let's draw this out. So let's say that's our triangle ABC. ABC. And let one side of it, namely BC, be produced to D. So we're going to extend this in a straight line further to D. He says that the exterior angle, ACD, is greater than either of the interior and opposite angles, namely CBA and BAC. And now we proceed to prove this. Let AC be bisected at E. So we're going to take this side AC and bisect it, which we know we can do by proposition 10. We call that point that bisects AC E. And let BE be joined and produced in a straight line to F. We're going to join BE. And we're going to join this. We're going to extend this over to F. And he says, let EF be made equal to BE. So he's saying that this is going to be made equal to this, which we know we can do by proposition 3. And we let FC be joined. We simply connect these 2 points. And let AC be drawn through to G. We're going to extend AC a bit over to G. And what's next? Then, since AE is equal to EC, the claim is that AE is equal to EC. Why is that true? Remember, E bisects AC, so those two line segments will be equal. And he says BE is equal to EF. This is equal to this. And why is that true? By construction using proposition 3, we made EF, when we extended BE, we made that equal to BE. So that's clearly true. And he says the two sides AE and EB are equal to the two sides CE and EF respectively. So let's check that. So AE is equal to EC, or CE, and EB is equal to EF. That's true. And the angle AEB, what angle is that? That's this one right here, is equal to the angle FEC over there. Why are those two angles equal? Those are vertical angles, which you recall we proved in the previous proposition are indeed equal. And check this out, we have two triangles. You'll notice we have two triangles here. So I'll just highlight those. Draw that a little bit better. So BEA and this other triangle over here, EFC. Notice that we have side angle side equality. Therefore, these two triangles are equal. And then we're going to make all of our inferences about the respective angles. And he says, therefore, the base AB is equal to the base FC. We infer that. Remember, this is using proposition number 4, side angle side. And the triangle ABE is equal to the triangle CFE. which we just said, and the remaining angles are equal to the remaining angles respectively, namely those which the equal sides subtend, which is just reiterating proposition 4. Therefore, the angle BAE, where's BAE? That's over here. BAE is equal to the angle ECF. ECF. And we note here that the angle ECD, that's ECD right here, is greater than the angle ECF. ECF. Why is that? By common notion 5, the whole is greater than the part, and ECF is clearly a part of ECD, so ECD must be greater. Therefore, Euclid infers that the angle ACD, where's ACD, is greater than the angle BAE. And why does he infer that? Remember, ECF is equal to BAE, which is that other opposite and interior angle in the triangle. So therefore, the angle ACD must be greater than BAE. And he says that you can just repeat this argument. Instead of using the side AC, you can bisect BC and just go through this argument once more. Similarly, also, if BC be bisected, the angle BCG, that is the angle ACD, can be proved greater than the angle ABC as well.